Hi guys, welcome back to another video on my channel, Gamma Di Gamma. Apologize for the break in the middle. As you all know, I have graduated. I should have a lot of free time on my hands, but I was, back home and doing all the things that I basically do at home. One good thing this time has been this improved microphone setup. I am now using the Blue Yeti, the coveted Blue Yeti microphone. Let's get started with this video. I shouldn't talk too much. Okay, so in this video I am going to do a double integral, and the change is, instead of explaining dynamically as I write, I am not going to be writing this time. I am going to explain what has been written. So the main problem to be solved in this video is evaluating this double integral, which I am calling I of n. Now n indexes the power in the denominator, and this is probably one of the only times we're going to do a double integral. We don't do them too often on this channel, but maybe we should. So we're integrating over a square region. 0 to 1, 0 to 1 is a square, is a 1 by 1 square in the xy plane. And that's why the variable of integration is x and y. Now, in the first step of this, I'm going to split this region. We can either split the y or the x. Here I'm splitting the y from 0 to x and x to 1. Now this may not be the most obvious strategy right off the bat, but bear with me, because once we draw this diagram, and where we see the diagonal line here, the dotted diagonal line in the middle is actually y equals x. So the first integral, 0 to x, y goes from 0 to x and x goes from 0 to 1, is actually just this yellow shaded region here. Now that's all well and good. The main thing here is we're going to actually change the order of the integration in the first integral. So instead of having the y first, we're going to have the x first. But that's not simple in this case, because the inner integral depends on a variable of integration of the outer integral. So for that to be done, we have to look at this diagram, which is, just here for us. Notice that y in this, if we look at y first, is going from, if we look at x first, because that's x is going to be inside now. If we look at x first, x is actually going from this point, which is x equals y, to the end point, which is 1, x equals 1, and then y is obviously doing the rest of the iteration from 0 to 1 here. So with that, we have integral from 0 to 1 in the y, and then x integral goes from y to 1, and everything else is unchanged. And then again, the second integral here is also unchanged. I've just used a different color to write it down. Now what I propose doing is interchanging x and y. So whatever's x goes to y, and whatever's y goes to x. I could have used different variables, but maybe this is bad notation, but I think this just drives home the point that change of variables does not affect, in this kind of change of variables, does not affect the definite integral. Now, so the x goes to a y, and the main thing to note is that the integrand is symmetric with respect to this kind of change, and that's what helps us throughout the problem, is this symmetry of x and y in the integrand mainly. So with that, I'm keeping the first integral as it is. We have twice the integral from 0 to 1 and y to 1 dx dy of the integrand. Now I'm going to introduce new variables. So I'm going to change variables. I don't think many people will have experienced a double change of variables. We've only used a change of variables in the one-dimensional problems. But let the variable u be x, y, and the variable v be x by y. I think there's a mistake here, which I will rectify right now. So let's see, like that. And then we have u is xy and v is x by y. With that, we have y is u by v, because if you divide them out, the x's will cancel and then you get y squared, which, you know, makes sense here. And x is uv raised to power 1/2. This is just simple inverse relationship between these change of variables. The main question, I think the most important question of this video, is how is this area going to change? So the area concerned still is this yellow shaded region, because, you know, if you check, it's, you know, x goes from y to 1 and then y goes from 0 to 1 is still this area. It's just the order got reversed. Well, the line A, actually, this base is actually the x-axis, which means it's y equals 0. I don't care about, like, if it's, you know, finite, it's limited to this meeting with B. I just care about the entire, like, line, which is y equals 0. And I can convert that into the u and v language. Y equals 0, according to our conversion formula here, is just u equals 0. Fair enough. B, the line segment B, is actually x equals 1, because this point is 1. So that means uv is 1, and I suggest you to do these to verify this for yourself. And then v is 1 by u. Fair enough. With C, we have x equals y, which is this diagonal line, and that gives us v equals 1. That's just the area, right? That's the boundary of the area, rather. We just saw what these boundary lines in the old area are being mapped to. Well, we found them out here on this side. Now we want to find the area enclosed. So region A, or the area enclosed by this line A, is basically on top of the x-axis. So that means y is greater than 0. That converts to u is greater than 0. Just by simple inequalities. Region B, we want x less than 1, because, you know, it's behind this x equals 1 line. So notice that x squared minus 1 equals x plus 1 times x minus 1 less than 0. If we have this inequality, this means that minus 1 is less than x is less than 1. But since x is greater than 0 throughout the problem, because you know, we're basically only in the first quadrant. In the first quadrant, x is positive. Therefore, x squared is less than 1 is equivalent to x is less than 1, which is basically the inequality we want. And if we convert that, we get uv is less than 1 from this. uv is less than 1, and then since u is positive, which we already established through region A calculation, v is less than 1 over u. Now region C, for region C we have y is less than or equal to x, or rather y is less than x. We're not considering the equality right now because it simply doesn't matter. That's just the boundary. U over v is 1 over 2 is less than uv raised to 1 over 2. Now we can cancel u from both sides because u to the 1 over 2 is greater than 0 and u itself is greater than 0. Therefore we have 1 over v to the 1/2 power less than v to the 1/2 power. Now notice that v to the 1/2 power is greater than 0 because again square roots we're considering them to be positive here. So we're going to have v is greater than 1 here, like that, just simplifying things. The signs are important. We needed to be careful throughout the steps because these are inequalities we're dealing with and not equalities where we can just take the sign for granted. If we multiply by a negative, we flip the sign of the inequality. That's why. And now armed with all these facts, we can draw a sketch of the region now in the UV plane. So, well, line A was, I believe, u equals 0. It was u equals 0, which is this vertical line here. Line B was v equals 1 over u. So that's going to be a falling 1 over u, a reciprocal function here, like this. And then C was actually a v equals 1, which is going to be this horizontal line, like this. Fair enough. And if we look at the region, the area enclosed inequalities that we set up, we have u is greater than 1. So that means, points above the u axis. Fair enough. That's basically most of them. That's not helpful. We need more. And that's why we have region B here. So region B was, let's see, v is less than 1 over u. So that is under the curve v equals 1 over u. That's under this curve that I'm highlighting. Fair enough. And we had the last one, region C, was v is greater than 1, which is basically on top of this line C, above the line C. So if you combine all of these results, you're gonna get this yellow shaded region, which sort of tapers to infinity as u goes to 0, as it should, because b is the exponential, is the reciprocal function 1 over u. Finally, with these change of variables, we have this integral. We have 2 times. Now the area actually is, let's see, v is going from 1 to 1 over u. So we have that. And then u is going from 0 to 1. Because again, if you consider the extent of this horizontal line, starts at 0. Even though the v value goes to infinity, that's fine. And it ends at 1 here, where the line B intersects with line C. So that point is 1, 1 on the UV plane. So that's 1. So it's 0 to 1. And here, in this gap I have left out, we have to put in the absolute value of the determinant of the Jacobian. Now that calculation I have done down here. So I found the du by dx, du by dy, dv by dx, dv by dy in a matrix, and then taken the determinant of that, which turns out to be 2v through simple calculations. And then again, it's under absolute value, so the minus gets absorbed. Now this isn't actually the determinant we want. I mean, we actually want dx by du and dy by du. So what do? Well, there's a formula that the determinant of the Jacobian inverse, because the one we wanted was dx by du, which is the inverse of this matrix here. So the determinant of Jacobian inverse under absolute value is 1 over absolute value determinant of the original Jacobian j that we calculated on top. So that's 1 over 2v. Fair enough. This is by the multiplicative property of the determinant. Then we can just plug that in here, in that factor in here. Perform there's some typos, apologize for that. I will try my best to rectify. There should be a u here, like that. And I should highlight this gap that I have left out. Okay, fair enough. Now, we first do the v integral because that's pretty easy to do. We get ln v from 1 to 1 over u. We plug that in. That actually nicely cancels out with this ln u factor. which was quite annoying in the denominator. And then we're left out with du over 1 plus u to the n plus first power, which, you know, can be evaluated using the power rule of integration. We end up with minus 1 over n times 1 minus 1 over 2 to the n. And that is the answer. Now I can go a little ahead and actually take the limit as n goes to 0 of I of n, which basically becomes this integral where the power of n is 0. So 0 plus 1 is 1. So there's power 1 for this 1 plus xy term. When I do that, I have limit as n goes to 0, minus 1 over n, 1 minus 2 to the n. And then I notice that this is of the form 0 by 0, so I can use L'Hopital's rule freely. I do that, I differentiate the numerator and the denominator, and I get 1 over 2 to the n ln 2 as limit as n goes to 0 with a minus. So we get minus ln 2 after taking the final limit, and that is quite a surprising answer. How is the natural log even coming up? Well, natural log wasn't really there in the answer for the non-zero n case. It's sort of a limiting answer as we take the limit. We can actually go on and do another integral, which uses the same strategy, which is the symmetry of the x and y, and you know, this interesting change of coordinates, change of variables. We have arctan of xy over xy times ln xy. Well, I'm not going to repeat too many of the things, but in the end, using the same symmetry, x and y symmetry arguments, we get 2 times integral 0 to 1 in the y and integral from y to 1 in the x. Then we introduce this same coordinate change. We get the same Jacobian factor because it's the same coordinates. We get the same region because that we had the same square, 1 by 1 square region to begin with. And we nicely cancel the ln u factor here, and we get a minus 0 to 1 arctan u over u du, which we can evaluate by writing the Taylor series for the arctan, which is u to the 2n over 2n plus 1 with a minus 1 to the n alternating factor. In the end, we get with this sum, pulling the minus outside, minus 1 to the n, 1 over 2n plus 1 squared, which is nothing but the Catalan's constant, g. And you see, that's basically it. That's how you solve these kinds of problems. Whenever you see an interchange symmetry between the x and y, and you see this suspicious looking natural log xy term in the denominator, and it's a region like this, a nice symmetric region like this, where you can use a diagonal symmetry across y equals x or some similar thing, you can go on and use this method, and mainly this substitution, this change of variables. And I think that's all I had for this video. Thanks for watching, guys. Stay tuned and peace out.